right. All right, parameter tuning. Okay. So when it comes to playing around with actually, in today's jargon, really maybe the word I should be using is hyperparameter now. Because in a lot of the other machine learning things, and it comes from stats, is like in neural networks, the parameters are like the weights, right? And then the hyperparameters are the things that you change, like how many layers, and that stuff. So here, I guess really I'm talking about like the hyperparameters, the things that you're changing about how it runs. Where, like in neural networks, it's the same thing. Like I've got parameters I can change before I hit run, but then it's like looking for the parameters for the weights that have good values. There are broad types of parameters, okay? There are symbolic parameters. These are things that have like discrete values most of the time. There's no ordering, no distance metric between them. And this would be an example of which selection we use, which genetic operators we use. These are like big modular blocks that we put in or take out of our whole system, okay? Imagine you had all the different pieces of your GA. You've got a pile of different blocks over here with all your selections, all your crossovers, all your mutations, all your fitness functions. I could take a little of this, this, and this. Those blocks are these, the symbolic parameters. I can change this one out and put another one in, and it should still work, right? So these are the parameters, and honestly, you don't really come across technically by the textbook, by what it actually says. These are called the symbolic parameters. Realistically, most people don't call them that. Most people call them like the selection strategy, the genetic operators.
Okay, so could I say, for an example, could we say, oh, I swapped out tournament selection for roulette?
Exactly. That's exactly it. And then there's the numeric parameters. These are the actual values I can go in and change, like, well, what's my tournament size? The types and kinds of numeric parameters you'll have will depend on the symbolic parameters, because if I'm doing tournament selection, I need to pick like my tournament size. If I'm doing roulette wheel, I don't. That's not a thing. If I'm doing certain types of mutations, maybe I need something, where in another type of mutation, I don't. So these can be continuous values, but not always. But these are the things that we can change. These are like the knobs that we can change. So if we go back to this example where I've got all these blocks that I can put together to build my GA, each of those blocks have a couple knobs on them I can play around with. Okay? Some of those knobs might be on like the more basic framework, like how many generations, right? What's the crossover rate? I guess that kind of goes with the genetic operators, but it's a little bit more like meta, I guess. So parameters with an unordered domain. Let's ignore this. I don't like it. So regardless of the parameter type, we set parameter values. So if we pick tournament selection, just like you were suggesting, well, that is our choice for the symbolic parameter. Again, no one really uses that word. Officially, that's the word. Realistically, if you go to Congress on Evolutionary Computation and you say symbolic parameter, chances are 99 people out of 100 will be like, what? What's that? And then a numeric 80% crossover. Well, symbolic are high level, numeric are a little bit more low level in general. All of these are like in generals. There's always exceptions to the rules, right? These are nitty gritty. And then once we set all of our parameters, now this part's important. Once we set all those parameters, all the symbolic and all the numeric, we have our instance of our evolutionary algorithm. If I leave it, I put a pin in it, stick it there, I don't change anything, I have my instance. I could change out a couple of things, set the parameters, stick it here, now I have a different instance. Yeah, we don't care about that. So here's where we have a problem. How do we pick our parameters? You know, we design top down, right? Our design layer, we want to optimize for the algorithm layer, application layer. This is a very abstract way of saying we are designing our system top down, and we're making our parameter decisions as we go. But what's the best one, though? Like, how do we find the best set of parameters? When optimizing our problem space, we use the word fitness landscape. And then we use the word evaluation in this context, and what's good is defined by a fitness function. So fitness is the quality of a result that an instance is giving us. When optimizing the parameter space, we use the word utility, and that's another search space. So let's think about it this way. Let's break it down. I have an instance, okay? And when I hit run, and you know, I've got a bunch of blocks here with some knobs. Right? And I tune it all, it's set. When I hit run, imagine we have some search space, right, that we are traversing. And this algorithm, as it's evolving, is going through the search space. So this search space is all possible permutations of cities, all possible combinations of zeros and ones. And when we hit run, this thing is then affecting this by like, oh, you know, it's traversing through the search space and oh, it's happy. There, it found it. Great. So that's the fitness landscape. And our instances run, and they do that. But that's on one instance. This is on one set of parameters, symbolic and numeric. If I change them out, we might get wildly different results. And we saw that. Who here noticed that on assignment 1? Oh, you change certain parameters, you got crazy results all of a sudden. Some way worse, some way better. It happens. Now, the problem is, here you are trying to tune all those knobs. You are becoming like the search function for the instances. So here's you. Bear with me. This is very scientific. I'm thinking. Right? I'm thinking. I'm looking at my instance, and then I'm tuning it, and then I'm tuning it, and then I'm tuning it. But I've kind of got this layered approach. Because I'm hitting, here, let's make this more, there, this is what we're doing. Where here I am playing with this. We can envision this in its own multi-dimensional space I'm representing here in 2 dimensions. Where as I change these values, this is moving in this space, which has implications in this space. It has implications on how it moves through this space and what the shape of this space is. How the hell? Like, I am now like multiple layers removed. What the hell? What am I going to do? What was your strategy? Right? Like, tell me, what were some of your strategies when you did this? You all did it on assignment 1, and you did something. You didn't just set 3 parameters, hit run, and go, okay, good. What'd you do?
Played with the global variables.
Played with it. More generations. Lower crossover. More crossover. You just tried stuff. Yeah.
Yeah, I was just gonna say hold the rest of them constant, mess with another one, and look at how well it did compared to start and finish.
Exactly. So here you are looking at this space, and you change it. And then over here, you're like, oh, you know, I got better results here, so I kind of like that. So I'm going to keep that, and then I'm going to change this. Oh, that made it worse. Okay, let's put that back. Well, I'll leave that the same, but then change this. Oh, that got better. That's kind of the strategy, right? But at the end of the day, that's a search space you're going for. You have no idea if the parameters you picked are good or not. Now, if you're a pragmatist, you're going to say, great, my boss hired me to give them a permutation of cities for their milk run. I set some parameters, I'm happy, I hit run, I got a good result, they're happy, I made money, everyone wins. Cool. Or you're like the pure person who's trying really hard to show that they've really tuned their thing and that they definitely got the best they could get and all that. They're going to go crazy on trying to tune the symbolic parameters. They're really going to search through this. And there's a couple of strategies people take for doing this. Realistically today, if you're doing that, they'll do, like, it's like a grid search. You know, like you try a whole bunch of different combinations, and there are automated ways to do it where you just got like a function that kind of like just keeps running it over and over and over and over and over, and then it tells you which ones are really good. But again, really all that did was replace this with a robot. I don't know. Now it's a robot. And sure, it might be a little faster, but it's still like, I don't know. Is it any good? I don't know. And the trouble is, raise your hand if you've heard the word combinatorial explosion before. That's a fancy way of saying, if I come along and I pick one instance and I get results, how many things do I have to compare it against? Nothing. I'm just happy with that. Let's say I make two instances. I'm like, well, here's this setting and then settings B. I hit run. Well, now I've got two things I compare. Great. I add another one. All right, well, now I've got to compare three. I add another one. Well, now I've got to compare that to everything else. And then I add another one. Every time I add a new thing, it needs to be completely connected. Every new thing I add like n minus 1 edges. No, I add n edges to it. Meaning that not after very long do you have to compare this instance to that instance, but this instance to that instance, this to this, and this to that. We're in trouble. Does that make sense? Because, great, you know, I can hit run on this 100 times and then just pick the best one and be like, great, I'm happy. But then, if I set this, or that, or that, or that, or that, how do I pick the best one? Well, you can't just get the median result. Like, you can't just get the result from this. You have to compare the distributions of these. And if you want to compare the distributions, well, how many do you have to compare? My God. It's getting crazy. So in optimizing the parameter space, we call it utility, and we use the word testing in this context. Yeah, okay. So here's common, typical values for your typical GA, your typical evolutionary algorithm. You'll have your crossover about 80-ish. This is, as a rule of thumb, this is a good place to start, if it's a GA. 80% crossover, population size of, I don't know, 100, maybe 1,000, depending on how big it is, you might think maybe you want bigger. Low mutation, you're going to want mutation definitely lower than 50%, and if you're doing GP, you're going to want it to be very low, like 5%. But after that, that's just your starting point. Raise your hand if you've heard the no free lunch theory before. 1, 2, 3, okay, not many. This is the idea that at the end of the day, we can prove that there's not one single algorithm that beats everybody. There's no free lunch. This one's good over here, but this one's bad over here. But this one's over here. This one's better over here, but terrible over there. There's always these trade-offs. There's no free lunch. There's no silver bullet strategy. So, imagine for a second I have a parameter where maybe this parameter is crossover. And let's pretend this parameter, realistically, let's say it's a numeric one because it looks kind of continuous, right? So maybe this is crossover rate. No, maybe this is mutation rate. Let's say it's mutation rate. Okay? When mutation rate is low, my evolutionary algorithm gets pretty good performance. But as I change it, it starts to have a really, it has a big effect on the curve of the performance. Cool? But then there's some that maybe don't really seem to have that much of an effect. Maybe I keep changing the population size from 100 to 200 to 300 to 400, and it doesn't really seem to have that much of an impact. But what's worse, though, is we now have a case of pickup sticks, where as soon as you change one, it affects the other one. You ever play those games where you have to match colors, but when you hit one button, it changes all the other buttons? And you kind of have to get all reds? It's kind of like that game. Where okay, well I want to make this one better than okay, that one changed to red, but these two also changed to red. Shoot. Well, okay, let's hit this one. Okay, now that one changed to red, but this flipped to blue. Oh no, how do we, yeah.
So you're basically saying as soon as you choose something on the red graph, the green graph could potentially just change.
Exactly. We now have this multiple dimensional problem. Imagine I show you, imagine I pick a point. Realistically, boom, I set this there. I've set my crossover rate to 60, I don't know. All I really get, I can now change another parameter, well that one's fixed, to get this. So as I move along this curve will also change. So in this context, it looks like, well, the parameter on the left, that one matters. It has an impact on the quality of my search, but the one on the right doesn't. But maybe once I get to a parameter, maybe once I set the parameter to here, it has a much bigger effect over there. So test some values out on a few runs to guide your decision. This is my strategy. This is the strategy I recommend for the most part in this class. Because otherwise, you're going to go crazy. Now, you're still going to have to do the comparison of your distribution, of your results. But the decision is start with the basic template ideas, 80%, low crossover, 1,000 generate, whatever. And then be like, okay, what happens if I up mutation? Okay, that was good. Okay, great. Now what happens if I lower crossover? Oh, that wasn't very good. That's the strategy you take. Exactly what Liam was saying. Raise your hand if that's basically what you did on assignment 1. Exactly. There you go. And that is the reasonable strategy. Because right here, this problem of deciding what the heck we're doing here is a hard problem. Doing this, we have these nonlinear interactions. This is the idea of that game, where you hit this button and then it turn all red, hit this one, it affects these ones, but then this one change, and it's that game. They interact in funny ways. That makes it hard. It's time consuming. Combinatorial explosion's a thing. If we're working in continuous space, right, okay, let's try a mutation rate of, or let's try a crossover rate of 50%. Okay, now 60%. Well, why didn't you do 55%? Why didn't you do 55.5%? Why didn't you, And you might say, does it really matter? Yeah, it could totally have a huge effect. So that's a problem. And here's the big one. And take note of this for your assignment 2. Typically, if you try to tune the hell out of your parameters, you'll tune them for one instance. For one text file of that data I gave you. You're probably going to get lucky on that assignment where you can probably pick some parameters that work really well for all of them. But with TSP, the values that you choose for the symbolic and numeric parameters might work really great on instance A. But as soon as you pick a different number of cities, a different problem, a different set of cities that you want to go through, those parameters might suck. They don't generalize very well. Which might be fine if you are just trying to optimize that milk run they got to do. But if you want to make a general purpose thing, you know, it's trouble. Trade-offs. Okay, so parameter setting problem. If we change the problems, okay, but we fix the parameters, and as we change the problems, imagine, this is kind of hard to visualize because of the context of the problems, but here, if we're modifying which problems we're using, and we fix the parameters, well, it'll, you know, some parameter, like those parameters work better on problems at that end of the spectrum versus that end of the spectrum. But if you fix the problems now, well, now you can modify the parameter values and, you know, they might have an effect. And this is on top of the fact that as soon as you move mutation rate, it might wildly change what the best crossover rate would be. The point I'm making here is this is a hell of a hard problem. And if you're sitting there frustrated thinking like, how the heck am I going to do these comparisons? You're right, that is the question. That is the question that troubles everybody. So when you're sitting there, like when you were doing assignment 1, did you ever think like, how the hell am I supposed to compare all these results? Did anyone ever think that on assignment 1? Yeah. And you're right, it's hard. It's a very difficult thing. So comparing the results are difficult. Parameter tuning is difficult. It's a hell of a thing. So there's automated approaches, meta-GA. You build a GA to optimize your parameters for the GA. And then, well, how do you optimize the meta-GA? The meta-GA? Turtles all the way. There's other things too, like SPO and FRACE and param ILS. These are like popular automated approaches. At least they were popular. Today, I think in scikit-learn, there's a bunch of built-in parameter space strategies, so FYI. Generate and test, an automated approach. That's another name, generate and test. But if you're thinking in the classic machine learning strategy, you know, raise your hand if you've taken machine learning. Really high, really high. Okay, so you've heard of training, validation, and testing, right? Now, here's why we do that. Just in case this wasn't, in case it didn't click, the reason we're doing that is I have this data. And if I train my algorithm on all the data, we're definitely going to overfit. So here's my model. I want to take, I don't know, half my data to train it, then the other half I will take to test it to get the result, and then I use the testing results to tell me how good it was, right? So this is your basic training and testing. Now we've got a problem. Because even if you're doing something as simple as k nearest neighbors, you have a decision to make. Right? You have to decide what k should be. If you're doing decision trees, there's parameters you have to pick. If you're doing support vector machines, there's knobs you got to tune. And as soon as you make a choice, we are adding bias to our results. Because here's what I would do. Imagine I hit run on this, and I go, okay, well, with certain settings, it gives me a result of, I don't know, 91%. Great. But then if I come here and change it, maybe it gives me 81%. So which one do you pick? 91, it's better, right? Yeah, but you picked it not because it generalized well, you picked it because it worked well for that parameter setting on this data. You don't know how it works in general. You've inputted bias into the strategy here. You were the process of changing this. So you now have degrees of freedom. You now have to go like, okay, this was better because I did this, right? So this is where validation comes in. Maybe you split it into thirds. I don't know. Where what you do is you use the validation as like your mini test set for helping you decide where this should be. So if out of here I get like 90%, 94%, 91%, which one do you choose? I'm going to pick the one with the settings that gave me this result. Now, I can use the holy, untouched, sacred test data. Get my results. Those are my results. If I'm happy with them, great. If not, tough. If you go back and start meta-tuning, you're adding more and more bias. You're affecting your results. You don't really know how good it is in general. You know how good it is on the data that you were testing on. Because you tuned that parameter to that data. But the spirit of the testing is, I've got my model, how does it do? So that's why we have validation as well. A lot of people kind of get fuzzy on that. But the validation helps us tune. Testing, so training is training. Validation helps us tune, and then testing is like, well, how good was it? If you skip that middle process, it's bad. You don't do that. So, one sec. In the context of evolutionary algorithms, we have to be careful about how we think about it. If we're doing something like GP to generate decision trees for something, yeah, we would want to do training, validation, and testing. If we're doing a GA to search the space of permutations, suddenly, like, well, training, that doesn't really make sense, right? Because, like, how do we validate? Like, there's no machine learning here. This is just a search. Like, it's a heuristic through a space, a meta-heuristic, a hyper-heuristic, a bunch of fancy words to mean the same thing. You had a question?
Okay. To clarify this beyond doubt, if you're tuning your parameters based on the validation percentages, is that still good or is there still bias?
No, well, that's as long as you then conclude based on the result on your test data. You do use the validation to help you pick, and then once that's picked, you take it with the settings that you're like, this is it, this is it.
Oh.
And then you pump it through test data that it's never seen before, and there you go. Now, mind you, this is idealized, right? Sometimes if you're working in problems that has very little data, you plug your nose, you do leave one out, and you hope for the best, and you don't do testing because there's just not enough data. But it's all we got. For example, if it costs $1 bajillion to get one data point, well, be happy with your 10 data points, and the only way you're going to ever get any training out of that is like leave one out maybe, and you hope for the best. It's still probably going to suck, but it's what we can do. You had a question, or were you going to?
I was more what's like a standard or rule of thumb split for the training, testing, and validation?
There isn't
Like,
one.
Yeah. Like 80-20 generally, or?
If you have a buttload of data, which I think is actually an official measurement, by the way.
Yeah.
There's such thing as like a butt as a unit.
It's like 400 gallons.
Yeah, it's something
They use
silly.
it to measure wine.
Yeah, that's exactly. Yeah, so a buttload, I'm not being silly. I mean, I am, but if you have a lot of data, just going like, I don't know, 33, great. If you can train on hilariously little data and get amazing results on your testing data, it's wonderful. If you're working with realistic amounts of data, like you're not Google who has everyone's everything, that's when you're going to start doing things like the various cross-validation strategies, like your k-fold and whatnot. K-fold is a great one, but you're not supposed to do k-fold on all of this. You're supposed to do k-fold. You separate training, testing. You go over here and you put your testing data in a box and you lock it and you leave it there. Then you do k-fold on the training data. So k-fold then kind of like systematically creates validation sets within it. And that's how it kind of like helps you pick.
Hopefully I can explain this right. When you said with the validation, we're going to tune everything up, and then we get the testing, that's our result. Did you mean, we're going to completely swap out all the data we have for something else for the very last test?
Exactly. That's when we go to the box where we put that holy, sacred testing data. We take it out, and then we have our box that we leave it alone. We don't touch it. We just very carefully take our data, drop it into the box, and get our results. If at any point you feel compelled, like, oh, I think I can get better results, no, bad. Don't do that. Someone should be poke you if you do that. Now, the only reason I'm going over that doesn't really apply here for thinking of a GA. What applies, the process is very generalized here, where it's like, okay, well, we test these things, and then we're like tuning our settings based on utility. So utility function, evolutionary algorithm, and test problems. Test problems, TSP instances. Evolutionary algorithm, my GA instance. And then utility function, how good were they? If we have a tuner, an automated strategy, maybe you're the tuner. You were the tuner in assignment 1. You had your implicit utility function of was it better? Right? So you were a part of this, but this process can be automated. So, now, how to compare results the right way. Here's what happens. This is a TSP run, okay? And very good people doing evolutionary algorithms, you've got your test problems in your evolutionary algorithm. You're going to run your evolutionary algorithm because it's stochastic, not random, stochastic. You're going to run it a bunch of times. And every time you're going to get different results, probably, if the problem's big enough. And maybe you take the best results from each run, you count them up, and you generate a histogram. Raise your hand if you don't know what a histogram is. Okay, look it up. That's a histogram. It basically is how many were in this range of results, how many in this range, how many in this range, right? So I would look at that distribution and be like, yeah, that's pretty good. My GA, I was getting good results, right? The biggest amounts were over here, I'm happy, that's good. But that's one instance. That is this. I just ran this same instance a number of times, took the best result, best point in this space, put them over here, I collected them, and generated a plot. Any questions so far? So, now I come along, and I get another set of parameters. And I hit run, and this is my distribution. That's a weird one. But I came here, I changed these, so it's a different instance. And then I run that instance without touching those parameters another n times. Take all their best points from here, put them over here, collect them all, plot the distribution, I get that. Okay? Do we understand where these distributions come from? You can generate the distributions of, if I run it 100 times, give me the best one. Maybe you take the top 10 because they're pretty good. Whatever, right? You've got a set of results. And then you change the instances, you change the instance by tuning the parameters. Great. If we're looking to solve the problem of the delivery people need the best thing, I don't really give a shit. All I care about is I hit run 1,000 times, I take the best one, I give it to them, and they go fantastic. If someone comes along and says, but how happy are you with those parameters? How happy are you? Could you have changed them and gotten better results? If you're very pragmatic, you say, I don't care, get lost. I made my money, leave me alone. If you're a keener, you might go, I don't know, let's figure this out. And you're all keeners, right? Yeah. For those of you that are not from Canada, because keener is apparently also a very Canadian thing. Did you know that? Like, if you tell that to an American, they're going to be like, what the hell?
I live here and I don't know that.
You don't know what it means? Maybe it's more of an Ontario thing then. Raise your hand if you've heard keener before. Okay, well, you're the weird one. No, I'm teasing you. It means like, I don't know, how do you explain it? Like, someone who wants to do very well in school, they're like, oh, I'm doing so well. That's a keener. So you want to compare the results. I changed the parameters and I got this distribution. Which set of parameters are better? Here's where we say you compare the distributions. If I did it again, I get another distribution. How do I pick which GA gave me the best results? You could say, well, which one gave you the best result? All right. You could say, which one gave you the best result on average? Okay. These are simple summary statistics we can use to inform decision making. But the right way to do it is to compare all of the data we observe from an individual instance. The distributions. We want to compare the distributions. If you've taken your intro stats, raise your hand if you've ever done a t-test before. Great. A t-test is a great little math hack for a quick and dirty way of comparing distributions. But there are a couple of funny little assumptions we have to make about our data before we can do a t-test. What are they? We assume they're normal distributed. Do we see a problem there? The middle one, definitely. Normal distributed means it looks like this. Oh, right? What else do we have to assume?
Equal variance.
Yes, and there's a number of other things that we need to assume too. But the t-test is like a trick to get us to compare distributions. Because doing it the more right way, for lack of a better term, the long form way, is really hard if you're doing it on pencil and paper. The good news is we have computers today that can do things really quickly. And in spite of that, people don't really teach you permutation tests. Yeah.
Isn't it once you get over 2 samples, you have to do an ANOVA test instead of a t-test?
It depends on how you do it, but ANOVA is a great, awesome alternative. But again, it makes like assumptions. Does anyone know has anyone ever heard of a Mann-Whitney U test?
Yes.
Cool. What is it? Who can tell me?
No.
No? It's kind of like a t-test, but it's non-parametric. It makes less assumptions, let's say. And so it's really good. And what's cool about the non-parametric ones, what's cool about like the statistics, when you do these, how do I explain this? Disclaimer video, I'm going to explain this poorly because I'm not a statistician. I'm just going to give you my intuition. And I'm probably going to use the wrong words a lot, and anyone who's a statistician is going to cringe. I'm sorry. When you do the non-parametric stuff, when you say like parametric, it's based on like, oh, what's the mean? What's the standard deviation of this? Now we can do all these. These are based on some information. But if we don't have those things, if we're not making assumptions about them, we can do non-parametric analysis. And non-parametric analysis is kind of cool because instead of like plugging it into a formula, like we don't plug our values in a formula and just number crunch. The non-parametric stuff is actually like algorithms. The way you calculate a Mann-Whitney U test is an algorithm. It's really cool. And what I like about these algorithms is, as a computer scientist, I'm a little bit more comfortable with algorithms than I am with fancy math symbols, right? Chances are, a lot of you feel the same way, right? And with the algorithms, I find it a lot easier to get the intuition as to what it's doing. Raise your hand if you learn the t-test and you're like, oh, I understand the intuition as to why this is the way it is. Raise your hand if you're like, okay, this is the magic function I use. Exactly. Right? So, the next topic is going to be introducing how to compare distributions. How to do it the right way. And if you follow along, which it'll be Thursday, right? Tuesday, right? Yeah, me too. If you follow along, it'll make perfect sense. And hopefully you will say to yourself, why the hell didn't they just teach us that? Because that makes sense.
Swear.
Yeah.
Just for maybe the people who are like less like knowledgeable about the t-test, would it be helpful maybe to mention that the assumption of variance can actually be checked with like a Levine's test?
There's a lot of other things you can do, but then people a lot of times will be like, well, I don't want to do that because we're just assuming it is, and we're plugging our nose and pretending. People are bad at stats.
Comparing distributions is the main thing that scares me in this course.
The next topic, it won't be that bad at all. Oh no.
I'm like, oh no, I don't remember what it's.
I closed slides and now, whatever. All right, I was going to open up the slides, but I guess I can't. So I'll see y'all later.